Hello and welcome. My name is Valentin Wolf and I will present you our paper, DeFlow Learning Complex Image Degradations from Unpaired Data with Conditional Flows. Image enhancement tries to recover high-quality versions from low-quality input images. While supervised methods have shown incredible results on this task, it remains a challenge to obtain accurate paired training data in real-world settings. Our work therefore deals with the unpaired setting, where only a set of low-quality images and a separate set of high-quality images are available. To tackle this problem, we propose DeFlow, a novel unpaired learning formulation for normalizing flows. DeFlow can learn the underlying degradation model from unpaired data, which can then be used to generate synthetic paired training data. In our experiments, we then train existing supervised image enhancement methods on this data. In doing so, we obtain state-of-the-art results on 3 different challenge datasets for unpaired image enhancement. So, how do we learn a degradation model from unpaired data? From a probabilistic perspective, a degradation model corresponds to a generative model for the conditional distribution of a noisy image Y given its clean counterpart X. Usually, conditional distributions are learned by directly minimizing the conditional negative log likelihood. However, this relies on paired data and cannot be applied in our case. Instead, we need to learn the conditional distribution just from its marginals. This is ill-posed in general and requires making assumptions. We do so by using a normalizing flow model with a specially constrained latent space. In particular, we enforce the latent space of the clean domain to follow a standard normal distribution. Further, we postulate the shift between the domains to be additive Gaussian in the latent space. From these assumptions, the latent space distribution of the degraded domain follows to be Gaussian as well. Now, given this latent space formulation and by using the change of variable formula, we obtain a tractable model for the conditional distribution of Y given X. This formulation also makes it straightforward to sample from the conditional distribution. We first encode the clean image X, then we randomly sample a shift vector U from its learned Gaussian distribution and add it to the latent encoding. Lastly, we decode the latent vector and obtain a degraded version of the input image. As the shift vector U is sampled randomly, we can simply repeat this process and obtain different degradations. This explicitly modeled stochasticity is a distinct advantage over current GAN-based approaches that only learn deterministic degradation models. Using the change of variables formula, we also directly obtain the marginal distributions for each domain. During training of the normalizing flows, we then jointly minimize the marginal negative log likelihoods of both domains using only unpaired data. As learning the full marginal distribution of natural images is a difficult task, we further condition the flow model on domain invariant features. By doing so, the model now only needs to learn the simpler conditional distribution of an image given the domain invariant features. In our application, we just use the low frequencies of the input images as the domain invariant features. We then give these features as an additional input to the flow model. Due to their domain invariance, sampling translated images remains feasible, as we can simply reuse the conditional features from the original input when decoding the shifted latent vector. To evaluate our approach, we trained DeFlow on 3 different challenge datasets for unpaired image enhancement. Each of those datasets features a distinct degradation type. The entire dataset features a complex and highly correlated noise. The AIM dataset suffers from strong compression artifacts, and lastly, the DEPIT dataset contains low-quality smartphone images that need to be enhanced. DeFlow is then able to learn degradation models for each of the unpaired datasets. We then train the popular ES-GAN model with the synthetic data pairs generated from DeFlow. Finally, we can use this model to enhance the real low-quality images and obtain visually pleasing results on all 3 datasets. Further, we conducted a user study to compare DeFlow against other handcrafted and GAN-based degradation models. We do so by training ES-GANs on the synthetic data generated by each method and let study participants judge the visual quality of the obtained enhanced images. The results of the study show that the DeFlow degradation model outperforms all other learned degradation models we tested against across all 3 datasets. Further, DeFlow is very competitive compared to the handcrafted approaches as well. Most notable is its effectiveness on the AIM dataset, where all methods, but especially the handcrafted models, were outperformed by a large margin. We invite you to have a look at our code and look forward to talking to you at the Q&A session.